Hey, it's Mr. Thompson, and this is going to be a first of hopefully not too many online lessons. We'll see how this goes. This first one, I'm sure I'll be learning a lot as we go, and hopefully you'll be learning a lot as we go too. One thing that I have to give you the heads up on, if this is a prolonged absence from school, I'm going to be behind in covering material. I don't know yet how I'm going to quiz and test you. At this point, I'm more worried about getting the information to you, and it's really up to you. So it's time to definitely put on the responsibility hat and wear it proudly. You're going to have to do some of this or a lot of this on your own. Another idea is, especially since in BC we're going to be behind and I'm not going to have as much time to review, you might want to invest in a Barron's AP review book, or there's others, Princeton Review. But that will be something that you need to think about doing. So we'll see how this goes, but I'm just going to give you through the notes. You'll notice I'm adding a new Canvas module that says to the effect online learning, and then it'll be unit this, unit that. Really, we have two big units. This unit now leads into the next unit on Taylor series, Taylor polynomials. This lesson is entitled sequences, but it's part of a bigger unit on series and convergence or divergence, and we'll get into all of those kinds of things. So we're going to give this a shot, and then I'll have to see about uploading this. So recording this now, and we'll see how it goes. Trying to make sure that I'm recording. We'll see. Yep, I'm minute 45 in. All right, so this is in section 9.1 in your text booklet. 9.1, problems 19 through 35, and I will move my hand out of the way as often as I can to kind of describe these. But there will be a lot of these notes pages where you're going to be filling in the blank. It kind of gives a structure and a goal for what we've got to cover. Let's go ahead. A sequence, as you can read there, is a function whose domain is set by a set of positive integers. So a sub 1, a sub 2, a sub 3, where that sub is like a counting number. Okay, a sub n would be the nth term. And we're going to denote that with the brackets there. A sub n would be a sequence. This is different than a series, which we'll start the next lesson. But a sequence is just a set of numbers separated by a comma, and you're going to use that counting number to generate these. So, example, write the first five terms of the sequence, where a sub n is 3 to the n. Well, when n is 1, that would be 3 to the first power, comma, n is 2, 9, 3 squared, 27, 81, and 3 to the fifth power, 243. Okay? Again, I would stop and say, are there any questions? If there are questions, think about how you want to try to contact me. I'm hoping that you're going to use the messaging capability in Canvas, because this is how I'm going to get messages out to you. This n with the exclamation mark is not a excited n, it's n factorial. You do recall this from pre-cal. N factorial is just, so let's say it's 3 factorial. It'd be 1 times 2 times 3. You're multiplying all of those integers up to and starting at 1, but stopping at n and multiplying. So when n is 1, it'd be 2 over 1. When n is 2, it'd be 2 over 2 times 1, which we'll simplify that in a bit. Okay? 2 over 3 times 2 times 1. And a lot of times I start with a high number and count down. You'll see why later, especially when we think about convergence ideas, and factorial is going to be a big thing that we need in the next unit too. So we'll simplify these in just a second. 2 over 4 times 3 times 2 times 1, and 2 over 5 times 3, 4 times 3 times 2 times 1. Well, hopefully you would cancel some of those 2's, cancel again the 2's, cancel the 2, you get the idea. 2, 1, 1/3, right, because 2 and 2 cancel, 2 and 2 cancel, 4 times 3, 1/12, and then 1/60. All right? So, first 5 terms there. Again, separated by a comma, just a sequence. Now, with these, we have to work backwards. They're giving you the numbers in our sequence. We need to think about a function rule that would get there. Okay? Now, before we start this, I'm going to review a couple ideas. The first idea is an arithmetic sequence. Some people say arithmetic because that's what it looks like, but it's an adjective, not a noun. So arithmetic, and that is a sub n. The nth term expression, a sub n, is a sub 1 plus, and then you're multiplying n minus 1 times d, where you've got a common difference d, and you've got that n again as your term that you're counting up, the first term, the second term. So a sub 1 plus, well, the first term, 1 minus 1 is 0, so that'd be that. 2 minus 1 would be the next term, so that'd be our common difference. And these look like they have a common difference because these are going up by, right? They look like they're going up by 5. So we can use that one as that expression there. So let's try that. Our common difference there looks like 5. So we'd get a sub n equals our first term, 3, plus n minus 1. Well, what's our n minus 1 there? Well, it's just n. Remember, these are going to have function rules just like these have 3 to the n, 2 over n factorial. Same idea. That's going to be part of that. Times our common difference, 5. Okay, I'm a-okay with that, but if you want to clean that up and multiply and distribute the 5, etc., you'd get 3 plus 5n minus 5. Combine like terms, you'd get negative 2 plus 5n. Okay? The next one, well, this is not an arithmetic sequence, is it? Because I'm not adding up to get from term to term to term to term. What does that look like we're doing to get from 5 to negative 15, and then again from negative 15 to 45 positive? Looks like I'm multiplying by, oh, I don't know, maybe negative 3. That is a geometric sequence. And the geometric sequence rule is like this. A sub n equals a sub 1 times r to the n minus 1. Here we're multiplying. In an arithmetic sequence, we're adding from term to term to term. Here we're multiplying, and that r is called a common difference. Well, here it looks like we're multiplying from here to here to make it negative 15. Well, aren't I multiplying by negative 3? Another way to do this would be r equals a sub next, let's say a sub 2, divided by a sub current, a sub 1, or even a sub 5 divided by a sub 4, right? It's always the next term divided by the previous term that you were at, if whatever you are from the next to the current. So that would be definitely negative 15 over 5, negative 3. Okay? So our function rule for that would be a sub n equals a sub 1 again is 5 times negative 3 to the n minus 1. Now, you could break this up and think about this, because a lot of times you're going to need this, especially in the next whole unit that we do. The geometric sums are going to be a big one, so this geometric sequence is an important beginning step here. I could break this up into 5, because it doesn't have an exponent, right? It's just 5 to the 1. But I've got negative 3 to the n, and negative 3 to the negative 1 power, right? See that? So negative 1 would just change that to be, right, if you're multiplying, you add exponents, so I'm unmultiplying, so I'm going to multiply there, adding exponents. That negative exponent makes that a fraction, so I've got 5 over negative 3. Well, let's just make that negative 5/3 times negative 3 to the nth power. So that would be another way of seeing that one. Okay? So two big ones, arithmetic and geometric sequences. Next thing is looking for a pattern here. Well, am I multiplying to get from 1 to 4 to 9? No. Am I adding something? Well, that difference is, in fact, if you did finite differences, you'd say 1 to 4 is going up by 3. 4 to 9 is going up by 5. 9 to 16, I think that's going up by 7. So we could do that if you wanted. If you remember doing finite differences, this would be in Algebra 2. 3, 5, let's see, that's going up by 7, that's going up by 9. Well, those look like they're each going up by 2, so that reminds us, oh yeah, that's probably, if the finite differences are common at the second level, isn't that a quadratic function? You're sure enough it is. A sub n equals what? Well, it's something squared. Oh, it's n squared, yeah. So it sometimes helps if you put, and I'll put this in another color here just so we can highlight it, above, where n equals 1, 2, 3, 4, 5. That will help you see your function rules there. a sub n, yeah, that's just n squared, right? N to the second power. Okay? This one also looks like it is increasing kind of a faster rate there, but it's not quite the same. In fact, if I think of this as 3, and that's a 3 squared, but something more. 3 squared is 27, 3 squared 81. Wait, isn't that more like 3 to the first power plus 1, 3 to the second power plus 1, 3 to the third power plus 1, etc.? So a sub n would be 3 to the n plus 1. Again, you're looking at these patterns. Some of these are requiring you to think about your number sense ideas. Okay, so a sub n is 3 to the n plus 1. Fractions. Well, if I think about these as counting here, we got 1, 2, 3, 4, 5. Sometimes if you just set up each of those as a separate numerator or denominator, what function rule would I need to get from a 1 to a 2, or a 2 to a 3, or a 3 to a 4? I think we're just adding, right, 1 to that n value. So that'd be n plus 1 on the top, okay, because those are just going up by 1. So if you think about the slope idea, n plus 1. These are going up by 2, so I need to say 2n. However, if I say 2 times 1, I'd get 2, but I only need a 1. 2 times 2 is 4, but I need a 3, so I need to... 2 times 2 is 4, 3. How would you get that? Subtract 1 and test each of those, right? So let's try the fourth one, the fourth term. 4 plus 1, that gets our 5 there, good. And 2 times 4, 8 minus 1, 7, 5 sevenths. Good, good, good. Okay? So again, a lot of these in this writing the expression, you're looking for patterns. You're looking for patterns to find those. All right? Now, a big topic that we're going to be thinking about the rest of this year. If a sequence, and later we'll apply this to series as well, and I'll start in on series the next time, has a finite limit here. If a sequence has a finite limit as n approaches infinity, we say that the sequence is going to converge. If it does not have a finite limit, if that a sub n term does not have a finite limit, then we're going to say that the sequence does not converge. Okay? So they've given you the first term, second term. This is called the general term. This is the nth term here. So what we're going to do is say the limit as n approaches infinity of n over n plus 1. And you guessed it, we're going to go back to needing all our skills from limits from the beginning of the year. Don't forget L'Hopital's rule if you need that as well. Well, I'm thinking as the limits here, the degree is the same, so the exponents are the same, divide the coefficients. That limit would be 1. There we're going to say, therefore, and you've seen that symbol before, so that 3 triangle thing, therefore, the sequence converges. We're not saying what it converges to right now, we're just saying whether or not a sequence converges or not, and that will become an important idea that we see later in further lessons. So again, this is kind of an intro, good starting point lesson. 1 over 2, 1 over 4, 1 over 8. Well, let's just take the limit as n approaches infinity of 1 over 2 to the nth. So 1 over 2 to a very, very large number. 1 over 2 to some very large number is effectively 1 over some giant number infinity. You got one cookie divided by an infinite number of people, you got no cookie. Right? So that's going to give us equals to 0. Again, therefore, our sequence would converge. Okay? We got 1 here, we got 0 here. Well, those are both finite number. Our sequence converges. Our next one. Sometimes it helps if you write these terms out. Right? 3 plus negative 1 to the n. Well, when n is 1, negative 1 is going to be an odd power there to the 1 power. That's going to be negative. That'd be a 2. Comma. 3 plus negative 1 squared when n is 2. That'd be positive 1. That's going to be 3 plus 1 is 4. And then an odd power 2, 4, etc. 2, 4, 2, 4, 2, 4. That limit, as n approaches infinity, of 3 plus negative 1 to the nth power, is d and e does not exist. That limit does not exist. You're not getting to a finite limit there. It's alternating. It's oscillating between 2 and 4, 2 and 4, 2 and 4. Therefore, we're going to say that the sequence diverges. Diverges. Okay? Let's try this next one. The limit as n approaches infinity of n over 1 minus 2n. Now, notice how the order, this denominator, it is not in standard form. If you have to rewrite that as limit as n approaches infinity, n over negative 2n plus 1, that's a giant number, divided by negative 2 times that same giant number, plus my salary, not very important right there. So it really, doesn't that just boil down to be 1 over negative 2 if we look at the leading coefficients? Negative 1/2, that is a finite number, therefore the sequence converges. This next one, if I take the limit as n approaches infinity of the log of n divided by n. Well, the log of infinity is infinity. And as n approaches infinity, and n would be infinity as well. Oh, wait! That does remind us, hopefully, of L'Hopital's rule. We're going to have to use L'Hopital's rule. For our purposes now, this isn't a formal show on an AP test. So if you just want to say that I've seen that it is the indeterminate state, I'm going to put the equal sign and I'm going to write L'Hopital's rule right above. How did L'Hopital's rule work again? Oh yeah, we're comparing now the derivative. So I'm taking the limit as n approaches infinity of, well, what's the derivative of log of n? As, with respect to n, that's 1 over n. And what's the derivative of n? Well, that's just going to be 1. So what's the limit of 1 over n as n approaches infinity? That's going to be 0. So even though it's infinity over infinity, that sequence has a finite limit. Those terms would converge to 0. Those series would, that sequence, I'm sorry, would converge. Therefore, the sequence converges. Next one, n factorial. Okay, oftentimes it helps to write these out. So before I take the limit, I'm going to expand this out. So a lot of times I would start with, well, this next one I'd probably start, well, I'll just count it up, right? So our pattern starts with this, 1 times 2 times 3 times ... times what? Well, I'm stopping at n. Okay. This next one, 1 times 2 times 3, ... right? I'm stopping at n plus 2. Well, to get to n plus 2, the previous terms to that would be times n plus 1, times n plus 2. You can see, hopefully, that the 1 and the 2's and the 3's, that's going to cancel. That's no problem there. But my last term here would be n. All of my numerator terms are going to cancel. So if we had, let's say, n is 3 or 4 or 5, something small, you could multiply those out and write all those terms out. If it was 5, 1 times 2 times 3 times 4 times 5, 1 times 2 times 3 times 4 times 5 times 6 times 7. So everything's going to cancel except for 1 on the top and the last two factors there, n plus 1 and n plus 2. Now we can take the limit as n approaches infinity of 1 over n plus 1 times n plus 2. Need a parentheses there. Well, isn't that going to be 0, right? Because it's bigger on the bottom. Therefore, the sequence converges. And our last example, n factorial. Sometimes it helps to write these with the what I would call the business end, the last term. So we'll do this time this way. N times n minus 1 times ... 3, 2, 1. We're counting down this time. So just another idea, if this helps you. It helps sometimes to show them this way because, again, all your excitement is going to happen with the n bits. The 1, 2, 3's better cancel. So n minus 1 is my last term. I'm stopping with that. N minus 1. And then be n minus 2. Well, that would be the next one up here. So n minus 2, ... right? dot 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 3, 2, 1. Well, the 3, 2, 1s again cancel, cancel. The n minus 2, the n minus 2, the n minus 1, the n minus 1. All you have left is the term there. So we'd have the limit n approaches infinity of n, right? That's the only one that didn't divide out. Well, the limit as n approaches infinity is infinity, therefore the sequence, or sorry, yeah, no, I said it right. The sequence diverges. Okay? At this point, I don't know yet anything about how I'm going to assess whether you're learning this stuff. My math lab is an option that I might be increasing the use of that. So stay tuned. But at this point, I just want to test out our system, and this is an easy lesson to start with. And 20 minutes is something that you can do. I'm hoping you get some chance to practice. Again, your homework is in your book, 9.1. 19 through 35 odd, and a lot of your homework will be worksheets, and I'll be scanning those as well for you as we go. Hopefully not for too long, but again, we'll play it by ear as we go. Hope you're having a good day. Take care of yourself, and I'll talk to you all later.